My name is Satwant Singh from Lattice Semiconductor. So I'll be emceeing or chairing this track sessions today. Our first speaker is Ken Foust, Intel. The topic is Developer's Guide to MIPI I3C Implementation. I3C is a new standard for sensor interface that we've been working at MIPI for a couple of years now. Let me introduce Ken Foust here. Ken likes to play guitar, but also can play drums. By the way, he has a full-time job at Intel. But sometimes he works on I3C as a work chair. Seriously, Ken Foust is a sensor technologist and researcher at Intel. He leads sensing initiatives across Intel's product portfolio and R&D labs. He's also the chair of the MIPI Sensor Work Group. Previously, Ken was a director at Kyonix. He started his career at IBM and received a BSEE degree from Alfred University. Please welcome Ken Foust.
Thank you. Am I coming through okay? Audibly?
So this is a move.
That's the lightsaber ignite.
There you go.
Nice.
There you go.
All right. Great. Thanks, Satwant. And also, Satwant is the vice chair of the Sensor Working Group and really kick-started this effort in the MIPI Alliance. I was enjoying myself in my little bubble at Intel when I heard of his Birds of Feather initiative and just had to join him because of how important I3C is for the sensor industry and mobile influence industry. So thanks, Satwant.
You're welcome. Keep it on.
So welcome to a developer's guide, to the right, thank you, of I3C implementation. A few things I'd like to cover is just a general introduction to MIPI I3C. So as you may know, we released an adopter version of the spec for people to start to review this summer. So if you don't mind, just a quick show of hands. Has anyone actually seen the draft MIPI spec that's in the industry now? So, all right, that's good. So if you're at least an adopter member of MIPI Alliance, you can gain access to that today. I'd also like to speak in some detail about the key features of I3C, and then share some implementation guidelines. So I've discussed MIPI I3C in a lot of forums. This is one of my favorite topics. And so you may have seen webinars that we've done jointly with the MEMS and Sensors Industry Group. And what we've never done is spoken in more detail about some of the key implementation guidelines. And they tend to revolve around legacy device support, the HDR modes, high data rate modes. You'll learn more about those today, and as well as the speaker after me we'll discuss those. Timing control, which is a new feature we're bringing, and the impact of varied topologies. So we're going to talk a little bit about that as well. And then I'll summarize some good design practices towards the end and answer any questions that you may have. So welcome to MIPI I3C. This is the mobile system diagram that I tend to use. And so what we're talking about is this interface right here. This is an exciting new interface connecting sensors and sensor hubs to application processors and other hosts. So the intent at a high level is to unify key attributes of I2C and SPI to likely familiar industry standard low-speed interfaces that are commonly used for sensors, and while also providing improved capabilities and performance. So if we did this right, we've developed a ubiquitous low-speed interface, as ubiquitous as I2C and SPI. So anywhere sensors are used, we feel that I3C belongs. And we've worked hard to continue to work hard within the MIPI Sensor Working Group to aim it towards historical I2C spine UART applications in a wide range of mobile-influenced industries. These are, for the most part, self-explanatory. Internet of Things, AR, VR, wearables, automotive infotainment, etc., phones, tablets, PCs. So what is I3C? Well, we started with a two-wire interface as a guide, and I'm just going to advance those. But we've added some key features that have been lacking historically, such as in-band interrupt, dynamic addressing, multi-master support, some standardized commands, timing control, hot join, and error detection recovery, while maintaining I2C compatibility as best we possibly can. We'll talk about that and kind of the role of I2C legacy devices in a little bit. We've made it lower power, so we can kind of pick and choose who we want to pick on here, but let's pick on I2C fast mode, which is 400 kilohertz in both of these instances. And with our standard mode and various high data rate modes, you can expect a fraction of the power and up to close to 100 times faster data rate by adopting I3C. So the key driver for this, as I'd mentioned when I was introduced by Satwant, was the proliferation of sensors in mobile. So this is a slide that is very, very old. You probably can't see it down here, but from 2012, back when Satwant was just a young fellow. When he was evangelizing this issue, and that is that the adoption of sensors is just exploding in the mobile platform, and it's creating some unique issues or headaches. Two of them are there are just too many I/Os. So if you now take the image here of the kinds of sensors that are on the platforms and envision what it looks like connecting them up to the host, you can see that so you have accelerometers and gyros, ambient light sensors, pressure sensors, compasses, maybe fingerprint, touchscreens, maybe ADCs, or even memory you can envision. And they have all of these GPIOs dedicated to them. You have 2 lines for I2C, but you also have interrupt lines connected, dedicated to these sensors, connected to specific GPIO. You have some, maybe some synchronization signals coming in to synchronize data collection across the platform between the sensors. You have maybe some active or enable disable interrupts or data ready interrupts. You also, we found through a survey, had a fragmentation of interfaces, I2C, SPI, some parallel interfaces, UART, it was fragmented. So we dared to envision a future where you condensed all of those potentially onto two wires, a clock and data wire in standard mode, and tie this together while maintaining I2C compatibility. As we found in our surveying and discussions with the industry, the I2C really is the strong incumbent in that those legacy devices will exist for some time. Incorporating an in-band interrupt capability, an ability for these devices to interrupt the host over these 2 wires. We've standardized a set of command codes for the industry to use and reduce pin count, and as you've seen previously, we've reduced power as well. So that was our vision, but as we continued to work on I3C, we found that there were more usages that would come into our scope, and as engineers, we want to address those. And then we obviously have to keep that in check as well, and not just continue to iterate and iterate. So some of these examples were the role of maybe a secondary master device, and this really works in both, or is important in both of these implementations. So you can envision, let's say, a master or application processor, and you may have a sensor hub, you may have a GPS IC, some significant silicon there, in addition to sensors, in this case, like the inertial sensors, accelerometers, magnetometers, and gyroscopes. But all three of these intelligent things would like to subscribe to that data. They would like access to that data. And so we developed a secondary master class device that can effectively have the bus passed over to it, and it can gain access to those sensors. It's encouraged to even sniff information on the bus if it needs to. And that also plays out here in what we call our IMU usage. Additionally, you can envision systems where you may have, let's say, two of the same sensor connecting up to an application processor, but one of them may detach. Maybe it's in a keyboard which detaches or something like that, or maybe it will be powered down completely on the bus. And so what we had done was developed a dynamic addressing capability. Those familiar with I2C will know that it relies on static or fixed addresses, and there can be collisions in the industry or devices that have the same address. And so we've gone ahead and developed that capability. So based on these additional usages, beyond just consolidating the interfaces, reducing pins, we added multi-drop and secondary master support, dynamic addressing, and hot join, and we really sped things up significantly, as you'll see. So let's talk in more detail about the features, and I'm going to start with really foundational I3C, and that's what we call SDR. This is the base interface here. So it operates at up to a 12.5 megahertz I2C-like clocking, but with the defined open drain and push-pull segments. So if you're familiar with I2C, it's an open drain bus, right? So you have a pull-up resistor which creates your ones, and then you drive it down low, which can really limit how fast you can go on the bus. So I3C SDR functions very much like that, except there are instances, for instance, for a start condition, the bus needs to be available. It needs to return to open drain on both of these lines, such that the master or an interrupting slave can drive this low. And then the first byte on the bus, the address here needs to be arbitrated, right? So there needs to be winners and losers, and you do that through by allowing open drain through that segment. So we support multiple classes of devices. An I3C main master. So this is the master that brings up the bus. It has all of the information and initializes the bus, and it can support HDR modes, or you can build a system which just supports SDR mode, if you would like. There's the I3C secondary masters, which can support HDR modes or just the standard mode. But the secondary masters effectively can have mastership. They can request mastership. It can be passed to them, and they can take the vast majority of the responsibilities of the bus. They can go read sensor data if given the information and directive, they could handle interrupts. Or an event can occur, such as an interrupt, and it can pass that back to the main master if needed. There are, I'm sorry, it's down at the bottom here. There are the I3C slaves, and they can support HDR modes if needed or not. So there can be SDR only slave devices, as well as legacy I2C devices of certain type, of which I will talk about in more detail later. So just real quick, Jim Rippey, this clock is not working, so, okay, so give me like a 10 and a 5. So, sorry about that. So let's talk about, at a high level, the dynamic address assignment. So it's a standardized procedure for assigning a 7-bit address, very similar to the static address that exists in I2C, but instead this will be pushed to you during initialization. But what comes with that is some requirements for the slaves. So 2 standardized characteristics registers, which are defined very clearly in I3C, as well as a 48-bit provisional ID that aids the procedure along. It allows the master to determine that you are the gyroscope. Well, the provisional ID as well as the 2 characteristics registers allows the master to know your gyroscope versus an accelerometer. You support an HDR mode or you don't, things like that. So in this case, legacy I2C devices, they just still use their static address. There's the in-band interrupt capability. So we allow a slave to issue a start condition on the bus. So drive SDA low while clock is high when the bus is available. The master provides the interface clock, so the slave doesn't have to have a precision timing capability. It just needs to transition data on the falling edge of clock so that the master can clock it in on the rising edge. It's pretty straightforward. There's priority in these interrupts. So the master assigns the I3C device an address, and what that number is will arbitrate if an interrupt occurs or 2 interrupts occur at the same time on the bus. So the device with the lowest address will get priority through the interrupt process. And so the master will process that and then go back and process the other device in the rare event that actually occurs. So the master, when there's an interrupt, there's a lot of things it can do. It can hack the interrupt, it can read back data, it can hack it and just not handle it right now. I think we've really developed a flexibility in this bus that's needed. Hot join. So small print definition here. This is a very tough one because hot join is kind of a new term that we're developing. We're avoiding hot plug because we're not standardizing connectors as an example. So a hot join device is a device that joins the bus after it's already been up. I think a good example is, let's say the PMIC or LDO shut down a sensor completely. It hasn't retained any of its volatile settings or register settings, and it gets brought back up, and now it needs to be discovered. It needs to be enumerated, and so we have a mechanism for that to happen. So in doing that, though, slave devices they cannot violate electrical limits that we define or disrupt activity on the bus. So we believe we're very clear about that in the specification and look forward to this feature being leveraged in the future. Not going into a lot of detail on error detection and recovery methodology, but which effectively does not exist at all in I2C. So we've made an effort to identify error types for master and slave error types, added parity, some CRC. You'll have to review the details of the spec to see exactly what's available for each mode versus SDR mode versus HDR, the various HDR modes. But I think that's a good advancement. So the common command codes, this was an important feature we wanted to add early on. So there's standardized command mode with an extensible set of MIPI-defined codes. So there's a lot of code space available for MIPI to expand as well as vendors to apply on their own. But it's a pretty standard set of broadcasted or directed read-or-write commands. Very easy procedure. And as they exist today, the standardized command codes, they tend to handle event, enable, and disable activity states, some payload management, I3C feature management, such as ones we've discussed so far, test modes, as well as I mentioned, extensible space. So let's talk about some implementation guidelines here with I3C up to this point, and I want to focus here on legacy I2C devices, as we've from the very beginning wanted to maintain I2C backwards compatibility as much as possible, and without really limiting the capabilities and performance we could achieve in I3C. And so let's talk about these key points right now for legacy I2C devices. So the devices that will certainly be compatible on the bus are FM and FM plus speed devices. So the 400 kilohertz and 1 megahertz I2C devices, which are the glut of the devices used in mobile handsets and wearables as an example today. But a key feature that they all should have is a 50 nanosecond spike filter, such that we can run I3C at 12.5 megahertz. So one of the key innovations here, and there's 12.5 megahertz really is a key speed, is that when legacy devices are present, we actually want to run the bus for I3C devices at speeds outside of the glitch filter, such that the legacy devices do not see the activity and therefore are not disrupted on the bus and are not disrupted themselves. So, as the glitch filter would work, simple spikes would just clearly not be seen on the data or clock lines, whether positive or negative in that manner. Now, the I3C devices themselves, they do not have this spike filter because we want them to see the 12.5 megahertz clocking and data go back and forth on the bus. So this is really important from an implementation standpoint. Also, clock stretching is not allowed. So clock stretching isn't, we found in our surveying of the industry and our own experiences, isn't extensively used. But clock stretching was put in place in I2C to allow the slave devices to hold the clock low if it needs some more time to execute on something. So if it needs to acknowledge a byte or it needs to return a byte on a read, it can extend the clock low. Well, in order to gain the efficiencies and speeds and performance, we really favor an I3C a push-pull clock. So we very much encourage that because, as mentioned, clock stretching relies on open drain on the clock. We want really nice, fast, crisp edges on our clocks. And then a few things that aren't used. Fastmo Plus, they use 20 milliamp open drain drivers. You'll see when reviewing the specification that we're not requiring 20 milliamp drivers. We require a minimum what work out to be approximately 4 milliamp drivers. Again, wanting to be low power, wanting to be more appropriate for mobile and mobile influenced, not drivers that are driving long traces in test equipment or some of the areas that I2C go. And then we do not use the 10-bit extended addresses. A lot of what we were trying to do with I2C is marry the physical with the logical. Once you have dynamic addressing, your logical address space doesn't have to be that large because physically you cannot connect 10 bits worth of unique devices to one I3C bus. So important implementation guidelines with respect to legacy I2C devices there. So now let's talk about the high data rate modes, which Alex after me will talk about as well in detail, but let me at least introduce those so that the few guidelines there make sense. So high data rate modes, and what comes with I3C today in the specification are effectively two unique modes, and we see these as extensible. So we provide a framework for entering the realm of HDR modes and exiting them in a standardized manner, and what you do in between there is your business, but you cannot break the bus while you're in there. So we have some standardized ones that come along with it. And those are DDR, so double data rate, and then a ternary symbol transcoded mode, which kind of split into two, one in the event that you have legacy devices on the bus, and one when you have a pure bus, as we would say, where it's only I3C. So the goal with these is to push the bit rate, right? So on top of our 12.5 megahertz clocking, can we get at or above 30 megabits per second at a fraction of the per bit power? Can we keep it simple? Right, so this was a very, very important for us, and as many people that are familiar with I2C know, 5 minutes, is that gate count is very important. So keep it simple, keep it low on gates. Maintain coexistence with legacy I2C devices. And so what we had done is we defined, as I mentioned, a standardized mode to enter HDR, and at which point, when you're in HDR mode, devices that do not support HDR effectively look for an exit pattern, a standardized pattern on the bus. So if you don't support HDR, that's fine. You ignore, from this point on, what's on the bus until you see that pattern. Once that pattern is seen on the bus, you're right back and looking for a stop condition. So double data rate, pretty straightforward. So if standard I3C and I2C is clocking data in on the rising edge, transitioning on the falling edge, let's just clock data in on rising and falling edge. And so we define that in great detail, as well as the protocol frame for that. So you'll see that in the specification. Ternary symbol transcoding, so given a two-wire interface with simultaneous switching of the line, so divorce yourself from the idea of a clock and data line. You just have two lines which can change. In the transition of those lines, you can encode 0, 1, 2, and 3, so ternary symbols. In a perfect world, getting you 3x now. The throughput as opposed to just 2x, such as in DDR. So again, you enter that mode, you send commands and data as you need to, exit with the same exit pattern, and stop. So what are some guidelines for HDR modes? Important ones. Well, enter HDR commands need to be supported. So every I3C slave device needs to recognize the enter HDR command and determine, okay, it's a mode that I support or I don't support it. If you do not support it, again, you need to look for the exit HDR pattern and then the stop condition that follows. So all the devices will need to do that. As I mentioned, so non-HDR devices will have to ignore the bus traffic until then. Another feature, timing control I'd mentioned. So there's an synchronous and asynchronous set of timing capabilities. Synchronous is very innovative. For some reason, letters aren't coming through here. So imagine you have multiple sensors that you've set off to go pull their data in time, and you get an interrupt from them when their data is available. Well, there's going to be latency, and there's going between when you started that, there's going to be slop in their own clocks. And so what can result is that you are waking up, the master is waking up to sample multiple times and going back to sleep. Well, with some simple capabilities that we've added, system designers can align all of those sensors in time such that the master wakes once, reads the data, and quickly gets back to sleep. Very, very, very neat. Asynchronous modes, on the other hand, are for when events occur just asynchronously in time. You don't know when it's going to happen, it just happens, and you need to be interrupted, and you need to be able to pinpoint when in time that event actually happened. There can be system latency in getting the interrupt and processing it in the master, and so we have 4 variations on that available, which are a basic capability. all the way to very high precision. So we put these here for the industry to use and leverage, and we look forward to seeing how they are adopted. Some guidelines there, and I apologize for going quickly here, is sensor device and clock accuracy is really going to impact how well we can keep time, or the master can keep time in these modes. So when an event occurs, the internal, or the sensor itself is going to have a counter, and its accuracy is going to be dictated by its internal oscillator and clocking capabilities. There will be drift and jitter. And so the idea is that we've created some standardized CCCs to exchange information between the slave and the master, such that the master can actually calibrate to errors inside the slave's timekeeping, whatever oscillator they end up using. Last, it's hard to see, okay. So last key set of guidelines here are varied topologies. And so I purposely don't have any units on here because I'm amazed at the various topologies that we can be asked to support. But what are some of the impacts on the bus based on the topology? So there's impacts on signal transition and transit times, which can impact how fast you can run the bus. So I say you can run the bus up at 12.5 megahertz, but depending on if there are legacy devices on the bus or not, you can run at slower speeds. If you need to drive a large network, you can slow things down. But in the case of legacy devices, there's some care you have to take. So SDA and SCL drive strength, we set a minimum drive strength of approximately 4 milliamps, but all the usual physical trade-offs need to be made. You can go weaker for lower power and less interference or EMI versus stronger for faster and larger topologies and loads. Trace length and material, again, go longer so that you can support all these new usages. As well as you have PCB and cabling concerns. So FR4 versus coax or something like that. SCL and SDA pad capacitance, I2C, maximum pad capacitance, 10 puff. That's how it's specified. That's not realistic. Typically, pad capacitances are in the couple of puff range. That matters when you're trying to drive larger topologies. Clock to data turnaround time, the time it takes the slave to receive clock data in and turn around and start driving the SDA line, as an example, will impact how you can get the most out of the bus. The legacy I2C devices that you choose certainly will. You must run at I3C speeds beyond the spike filter or run at the speed of the legacy I2C device. So if you make topology and system trade-offs which doesn't let you run above the spike filter of the legacy I2C device, then you're going to have to slow the bus down. You can still use a lot of the features, but you will have those trade-offs to make. As well as another one very obvious, anyone that does this, is device location. So this here is a great diagram. So what is the impact of having two devices out on the end, let's say 20 inches away and then one just an inch away? So you're going to have reflections to deal with, etc. This is all physics. It's not black magic here. So in summary, thoroughly understand the capability of your legacy I2C devices that you plan to have coexist with I3C. Special focus on their spike filter and clock stretching. If leveraging timing control, choose an appropriate device mode that matches the requirements for your application with device capabilities, right? So a device's internal oscillator accuracy is going to impact how well that capability performs. And then lastly, understand bus topologies and all the impacts. This is very much physics bounded. single-ended interface. Any questions? And Jim, please manage time with the questions. Yeah. Thanks.
One question was just about broadcasting. So say you have one address which maps to multiple sensors, and they have a default address, but they also have a broadcast address. And then when you send a command, they would go to all.
Yeah, if you can please repeat the question.
Yeah, good point. So that's a great question. Do we support broadcasting of commands to all the devices as opposed to pointedly addressing them? Yes, we do. And so many of the commands work in a directed or broadcasted manner. And one thing we're looking at as well is the ability to kind of subgroup commands as well. So that's something very up to the minute that we're thinking about. But absolutely, we saw that as key. If the master wants to go to sleep or wants everything to go to sleep, just broadcast the intent and everyone go down, as opposed to individually saying, okay, I need to set this bit and that register on that device, and yeah, exactly. Good.
Any other question?
Well, I'm here all day today.
I may have a quick one.
So,
can you maybe tell something about the timeline, either of the spec release or maybe the adoption in SoCs and sensors?
I can a little bit. So we're in first draft review, which is getting us really good feedback on the specification as a document. So we've been working on this for a long time. We're very close to the project. And so we've gone into first draft review. We've published for adopter companies. We're getting good feedback to make this a better specification. Also, in our charter, as a working group, early on we acknowledged that this sensing is still very fluid and very dynamic. There's still a lot of innovation going on in the space. And so we still do try to manage inputs such that we can slide things in as needed. So if there's a target use case for it that we didn't think of, and there's a simple feature we could add, we've been trying to accommodate that, but we have less and less time for that because we intend to publish the spec by the end of the year. So being the middle of September, we don't have much time. And there's been great interest in I3C since the start. I would say, if anything, we wish we could have gotten it out faster because of the amount of interest and the number of people that we understand are intending to adopt it. I don't mean to brag, but inside MIPI, we might be the most followed working group. 596-ish people on our reflector. So,
one more question.
Last question.
Given your experience with MIPI working committees and so on, given that you're in the first draft review right now, when do you realistically expect, some SoC coming out with an I3C interface that will, work with a accelerometer or gyroscope?
Right. That's tough. I mean, I certainly won't speak for Intel there or others. But if you look at the sensor industry, so before I joined Intel 5 years ago, I was at Kyonix. I was the director of product engineering. I made MEMS sensors, accelerometers, and gyros. And we had to be very quick. A MEMS sensor element or a typical sensor element will last multiple generations of application-specific IC that's co-packaged with it. And those ICs can be spun every 8 to 12 months. And so we do expect pretty quick adoption on the sensor side. On the SoC side, I would say the more simple the device, the sooner it will be to market. Obviously, it takes longer for very large CPUs to bring new capabilities to the industry versus like a microcontroller. And so if you look at our working group makeup, I mean, we've had sensor vendors involved, obviously, at various stages, MCU people, STMicro, NXP, Qualcomm, NVIDIA, Intel, et cetera. So sorry I can't give you a date, but we expect it to be soon.
Thank you very much, Ken. Good presentation.
Great.
Yeah, thank you.
Thank you.